My name is Joe Keddy, and I'm a professor of soft matter physics here at the University of Surrey. And I'm also a Royal Society Industry Fellow. And as part of my fellowship, I'm spending 50% of my time with a small company called Pulpex. Every day, 1.2 billion plastic bottles are manufactured globally. And in the UK alone, 700,000 plastic bottles are littered every single day. So everyone wants a solution, no one wants to use plastic. But what's the alternative? I'm working with Pulpex, who have developed a paper bottle. And this is an alternative to conventional plastic bottles to hold liquids. It can replace things like PET, but it has 30% lower carbon footprint. So even the manufacturer of it is more sustainable. And importantly, this bottle can be recycled in the existing waste streams with paper. So there's no problem whatsoever in recycling it. And so in our work, we're looking for alternative materials so that if the bottle isn't recycled but goes into the environment, it'll degrade naturally. One of the candidate materials is called chitosan, and this is being made by a small company in Scotland. And this is a natural type of material that can be derived from crustaceans or shellfish. So in fact, their factory is located near a seafood manufacturing where they're processing scampi. So they can extract from the waste shells. Essentially, it's a type of carbohydrate material, which we're now developing as the barrier layer. And so things we're doing in our lab is investigating different ways of depositing the coating and also looking at its properties. So how fast does water flow through the coating? What can we do so it's even more watertight? The ultimate vision of our research is for us to walk into a supermarket and see these paper bottles on the shelves.
My name is Judy Lee. I'm a professor at the School of Chemistry and Chemical Engineering. Each day, billions of litres of household wastewater are sent to the wastewater treatment plants. These wastewater contains a lot of micro and nanoplastics, and if not recovered, then wastewater treatment plants could be releasing millions of micro and nanoplastics into the inland waters and the sea. A lot of products we use contain microplastics, such as sunscreens, cosmetics, facial scrubs, disposable wipes, washing sponges, and clothes. So when we wash our hands in the sink, take a shower, or wash our clothes, these microplastics get flushed down the drains and end up in the local wastewater treatment plants. Alarmingly, 50% of microplastics found in wastewater treatment plants are fibres from laundering washings. More than 700,000 microplastic fibres are released in a single wash of clothing. These microplastics can break further to even smaller micro or nanoplastics, making them difficult for current wastewater treatment plants to capture them. Filters are prone to clogging, so more research is needed to develop new filters and to understand how clogging occurs and how to prevent them. Our research focuses on the use of membrane filtration technology to recover these microplastics so they are not discharged into the environment. We want to understand the impact of different sizes and amount of plastic in water and how they impact the clogging of filters and ways to minimize the clogging. In the future, we would like to have our membrane filters installed at wastewater treatment plants to capture the micro and nanoplastics before they are discharged into the local rivers.
Hi, I'm Dr. Iman Mohaqiqian, and I'm Associate Professor in Mechanics of Material at the University of Surrey. We are focused on plastic waste challenge in high-performance sectors like aerospace, automotive, and energy industries that rely heavily on advanced plastic and composites. These materials, particularly carbon glass fiber reinforced polymers, are lightweight and extremely durable, make them ideal for improving fuel efficiency and lowering emissions. But while they help reduce environmental impact in use, they also create a major waste problem at the end of life. The issue lies in composite material themselves. Composites are often made using thermoset plastic, which cannot be remelted or reshaped. So when the planes or wind turbines blades reach the end of their service life, typically around 25 years, they become very difficult to recycle. On top of that, 30 to 40% of composite material are wasted during manufacturing, creating an immediate and growing problem. Right now, approximately 85% of composite material are not recycled at all. They are all landfilled. For those that recycle, the most common recycling method is pyrolysis, basically burning the plastic to recover the fibers. It's energy intensive and not environmentally friendly at all. Our work focuses on unlocking the potential of recycled carbon fiber by expanding how we think about its value. Right now, recycled carbon fiber is underused, largely because of concern around its mechanical strength. We are aiming to leverage not just the mechanical property, but also the thermal and electrical property of carbon fiber for second life application. By doing this, we can open new markets and create demand, which is critical for making recycling economically viable. By cutting down waste during manufacturing and making reclaimed material valuable, we reduce our reliance on virgin raw material. It is about building a circular economy for composite, one where advanced plastic don't become advanced pollution.